Okay, year 10 physics. So today we're going to be looking at AC generators. So keep in mind that we've already looked at magnetism, both permanent magnets and electromagnets. And then we looked at electromagnetic induction, which is when you move a piece of wire through a magnetic field. It induces an EMF in the wire, and if that wire is part of a complete circuit, you get a current. And so today we're building on that. We're moving from electromagnetic induction, which is also called the generator effect. And today we're moving on to generators themselves, AC generators. So you might be wondering, what does the AC and AC generators mean? I think you might already know this. So we have AC and we have DC, and that just means alternating current versus direct current. So if we look at direct current first, this is the one that everybody's familiar with. And this is just batteries provide direct current. Basically, they're always pushing electrons in the same direction so that the current is just always constant. You get a nice constant current when you're using batteries. They're always going in the same direction. However, when you plug something into a wall socket, all of the wall sockets in your house have alternating current in them, which means the current in them is going one way and then the other way and then one way and then the other way. And it's doing that 50 times or 60 times, I believe, every single second. So every second, the current alternates back and forth 60 times when you plug something into the wall. All right, so that's just the difference between AC and DC. And then we get to generating stations. So if we're talking about AC generators, these are all generating stations. And these are the places where the electricity that we use in our homes and our businesses is generated. And so we can see in the top left over here, we have a hydroelectric dam. And so this just uses the energy of the water stored up top to, as it falls down, they use that kinetic energy of the water to turn a turbine, which then turns a generator. And over here we see wind turbines. So here we have wind that's moving these turbines, and those turbines then just turn a generator, which generates electricity. And same thing down here, we have, these are tidal generators. They make use of the tides going in and out every day. And basically, they just have these red turbines here that the water ends up spinning, and then those turbines end up spinning a generator. And the same thing in the bottom right over here, we have, those are smokestacks from which is probably from a nuclear power plant. And in a nuclear generating station, all they do is use nuclear fuel to basically heat up water inside a closed system. When you heat up water, it turns to water vapor and takes up a lot more space. And they use that increase in volume to turn a turbine, which then turns a generator to generate electricity. So that's what all those things have in common. So turning motion into electricity, a rotating coil generator. So this is the one that you need to be familiar with. Something that looks like this, a simple AC generator. This is a very simple rotating coil generator. So you can see this blue thing in the middle is the coil itself. So this blue thing right here is the coil. And here we can see that our coil is only made up of a single coil. Whoops, what happened here? So this, we have one single coil here. Normally we'd have hundreds of coils, of turns of wire. Here we just see a single turn. Anyway, so just to point out a few things about this simple AC generator, you notice we have our coil of wire, which is somehow going to have to spin. Something is going to have to make the spin, whether it's the wind or a hand crank. You could use your arm, or it could be anything like a turbine that in a coal-fired power station or a nuclear-fired power station. Anything, something has to be turning that coil. And anyway, so also, actually, before I move on, notice these things down here called slip rings. So these two things, these two rings are called slip rings. And you'll notice that they have these graphite brushes that are touching them. It's hard to see in this picture, but these two little things are little graphite brushes that are always in contact with these spinning rings. So as they spin, basically these little graphite brushes just maintain contact. And the only point of those things is to allow this coil to rotate without tangling up wires, essentially. We'll see this again in a little bit. I have a better picture to demonstrate this. Anyway, let's just think, let's just look here for now. Let's consider this piece of wire right here, this one on the right side. And you can see at the moment, this one on the right side is moving downward at this instant because this is rotating in a clockwise direction. Okay, so if this side right here is moving down at the moment, using our right hand rule, remember, if you point your fingers from north to south, so hold your hand so that your fingers are pointing from north to south. So your fingers should all be pointing to the south. And then put your thumb in the direction that this piece of wire, that this part of the coil, put your thumb in the direction it's moving. It is moving down. You can see that. So if you put your fingers facing the south and your thumb pointing down, you'll notice that the palm of your hand is now pointing in the direction that this red arrow is pointing. And that means the current in this side of the coil will be going this way. And the same thing goes for the other side of the coil. You can see that this side of the coil is being moved upward in the upward direction right now. And again, you point your fingers north to south, you point your thumb up, and you'll see that the palm of your hand is then pointing in the same direction as this red arrow over here, which is this way. So you can see the current at this instant is flowing, if you're looking down, is flowing in a clockwise direction around that coil. Okay, we'll leave that at there for now. We'll come back to that in a little bit. So just notice again, a generator requires three things to work. And we can see in that picture that there is definitely a magnet, there's a coil of wire, and something has to be providing rotational energy. Something has to be rotating this coil. Okay, and when we do this, when we have a generator in this way, we get continuous AC, alternating current electricity, and you'll see in a minute why it's alternating. Okay, and keep in mind the whole reason that this is working is because of electromagnetic induction, also called the motor effect. And here's another example. So these blue arrows are representing the field lines. So you point your fingers in the direction that the arrows are going. And then this piece of wire is being pulled upwards. And this, whoops, it's being pulled upward in the direction of this red arrow. So if you point your fingers to the right, same as those blue arrows, and you point your thumb upwards, you'll notice that the palm of your hand is then pointing in this direction, and that is the direction that the current is going to be pushed. So that is electromagnetic induction, aka the generator effect. And that's how rotating coil generators work. They use this principle. All right. Moving down, so I'm just putting a reminder in here. Don't forget that something has to be turning a generator. You can see in this particular picture that there's a hand crank. So you would use your hand to turn this generator. And we actually have a hand turn generator that we've seen in the classroom that lights up a little LED light, similar to that one. Okay, so now back to the direction of the induced current. So we've already seen, we just talked about the fact that we can figure that out by our right hand palm rule. I should probably add that right here, the right hand palm rule. And just so you know, later on we'll see that the book and in IGCSE, Cambridge usually use something called Fleming's right hand rule to determine the direction of the induced current. Take my word for it, that is much more confusing than my method of using the right hand palm rule. So I'll explain the right hand, Fleming's right hand rule later on, but for now, just use this palm rule because it's a lot simpler. Okay, so here we go. Here's another generator right here. We can see that this one is rotating. If you're looking this straight onto it this way, you can see that it's rotating in an anti-clockwise direction. So we can see that on this part of the wire over here, this side of the wire is moving up, while this side of the wire is moving down. Okay, so we're just going to zoom in on this part of the wire right now, right here. So here's that same part of the wire right here. And just notice, remember, the motion, currently this side is moving up. That's what this arrow is representing. The motion is going up. You can see the magnetic field. We have north over here on the left, and we have the south over here on the right. So our finger should be pointing from north to south. So along these field lines, your fingers point this way. Your thumb points up in the direction of the motion. And the palm of your hand is the result. And the result is a current that ends up flowing through that wire in this direction. Okay? And there is the rule that we're using, the right hand palm rule. So your fingers point in the direction of the magnetic field. Your thumb points in the direction of motion, the direction that the wire is moving. And the result then, the current, the induced current, ends up pointing in the direction that your palm is pointing. And that's the right hand palm rule. Okay, so that we've just considered this part of the coil on the right hand side. But what about the part of the coil on the left hand side? Well, let's take a look at that one. So here we go. We're going to zoom in now on this coil, on this piece of coil, which is moving downwards. So it's moving downward, and again, the same magnetic field. There's a north on the left side, a south on the right. So here we go. Here we're zoomed into that same piece of wire right here. So again, oops, I drew the magnetic field lines the wrong way there. Anyway, let's look right here. If you point your fingers from north to south, so point your fingers this direction, and then you point your thumb down. So point your fingers from left pointing towards right. You point your thumb down because that's the direction that this part of the coil is moving. And you'll see that the palm of your hand then ends up pointing in the same direction as this red arrow. And that means the current is then flowing this way through that part of the wire. So already we can see that on the right side of the wire, the current is going up or this way. And on the bottom side or the other side of the wire, the current is going the opposite direction. So we're getting a nice clockwise motion of current here, which means we get a nice clockwise motion of current in this coil in that instant. So now what I want you to look at, let's just go back to this picture. Now consider what happens when this wire on the right side, which we've already determined has a current going this way. So the current is moving this way in it. So what happens when this piece of wire comes over and ends up on this side? So basically when this thing turns over 180 degrees, now this wire is way on the left side. Okay, so what changes? Our fingers are still pointing in the same direction. The magnetic field is still from north to south. So the magnetic field is still that way. The only thing that changes now is that our thumb used to be pointing up when it was on the right side, but now that it's moved over to the left side, now it's moving down. So if you flip your thumb over, you'll notice that the current is now going the other way in this coil. So the point of all this is that, just notice in this one single piece of wire here, in this one piece of wire, current was going this way in it, but when it rotated 180 degrees in that very same piece of wire, now the current is going in the opposite direction in it. So when it was over here, it was going towards the top of the page, and then 180 degrees later, once it flips over, now the current in that very same piece of wire is going in the opposite direction. And that's why we get alternating current, because the current in the wire keeps alternating directions every 180 degrees. There'll be a video at the end of this that I suggest you watch that really demonstrates that a lot more clearly than I think what I'm explaining right now. Okay, so again, just to highlight, what are those slip rings and brushes for again? Again, all they do is they allow these slip rings right here, they allow electrical contact to be made using these carbon brushes. So these are always in contact with these slip rings. As these slip rings are spinning, these carbon brushes are just maintaining electrical contact with them. And basically, if we didn't have that setup, if we just had wires without the slip rings, like a straight wire going to your external circuit, if we just had straight wires, what we would end up with is something like this. You would just get super twisted wires in no time at all, and eventually it would just break, and it would be useless. So slip rings and brushes allow the coil to spin without the wires becoming all tangled up. Okay, so now, what are the factors that affect the size of the induced current? What if we wanted to create as big a current as we possibly could? What do you think you'd want to do? Well, you'd want to do these 4 things. You would first want to rotate the coil faster. The faster the coil is cutting the field lines, the greater the EMF is going to be induced. So that's one thing. The next thing, you could use a stronger magnet. If it's all about moving a wire through a magnetic field, well, it makes sense that a stronger magnetic field would induce a larger EMF also. So you can rotate the coil faster, use a stronger magnet. You could have more turns of coil in the wire. For example, all the ones that we've looked at so far, like this example as well, same thing. We just have, basically, this is just showing one piece of wire as the coil. But really, you would have, like I said before, hundreds, if not thousands of coils of wire going around and around and around and around and around and around. Basically, every time you double the number of turns of wire, you're doubling the induced EMF. And the last thing you could do is have an iron core inside of the coil of wire. And basically, what that iron core does is it really strengthens the magnetic field created by these north and south poles. So having an iron core just really intensifies the strength of the magnetic field without using a stronger magnet. So those are the 4 things you can do to increase the magnitude of the induced EMF, or you could say the induced current. Okay, let's take a look at a quick animation of what is going on here. Let's see. So here we go. So here is an AC generator. And you can see, so as this generator is spinning around, let's just pause it, let's say right about here. Okay, so let's take a look. Let's focus at this, at the top part. Let me see if this works. Can I use this? Yes. Let's just take a look at this top part. Okay, I'm not sure how to erase that now. Anyway, this top part has a current moving through it. Oh, no, sorry. So we're, again, okay, let me just start this over. We're considering this top part of the wire. It is moving in this direction at that instant. So if you point your fingers downward, because you can see that these magnetic field lines are pointing downward. So point your fingers down, point your thumb in the direction of this arrow, and you'll see that the current in this side of the wire is moving that way. And now let's look at the bottom part of the wire. You can see, again, your fingers are pointing down because the magnetic field is still down. But now this part of the wire is moving out this way. So point your thumb in that direction, and you'll see that the palm of your hand ends up facing this direction. So if I let that play again, oh, how do I turn this pen off? No way to turn the pen off. Okay. Anyway, we'll just go back to the OneNote. Okay, so now let's consider the induced EMF, how that changes as the coil generates. So as the coil rotates, sorry. Okay, so let's see here. So we're going to start right here in this first position. So you can see right now, if this wire is turning clockwise, as this is saying, this wire is turning clockwise in each case. So initially this top, so we'll just consider this grayed part of the wire up here. So this part is initially moving in this direction. At that instant we're looking at it, it's moving in this direction. So you'll notice, is this wire cutting any field lines at that instant? No, it's not cutting them. It's moving in the same direction as them. So it's not cutting field lines at all. And that is why initially, so the EMF associated with that is 0, because it's not cutting field lines at that instant. It is moving parallel to the field lines. Now let's consider 90 degrees later. 90 degrees later, this gray part of the wire is now moving downward at this instant. So it's moving down, and at that instant, it is cutting the maximum number of field lines it can cut at that instant. And so that's why when we look at this graph, at that instant, it is a maximum induced EMF because it's cutting the field lines at the maximum rate it can. And then let's look 90 degrees later. I'm sorry, no, we're looking, well, sorry, again, yeah, 90 degrees later. So now this gray piece of the wire is at the bottom, and it is at this instant, it's moving this way at that instant. That's why at this instant, we can see it's not cutting any field lines. This piece of the wire is moving parallel with the field lines. It's not cutting them, which is again why the induced EMF is 0 at this instant. And then let's look 90 degrees later. So now, again, we're following this gray side of the wire. At this instant, this gray side of the wire is moving upwards. This gray side is moving up, which means it's cutting through all of these field lines. It's cutting through them at the maximum rate possible, which is why at this instant we get, at this instant we get a maximum, the same maximum, but in a negative number. So again, over here when it was a maximum and positive, we're getting the same thing over here, another maximum, but it's negative. And the only reason that that is negative is just because current is moving in the other direction in that wire. So let's just go back to this 0 state for a second. So if the field line, so if you point your fingers, again, we're considering just here right now. If you point your fingers from the north to the south, so point your fingers to the right side of the screen, and then you point your hand in the direction, sorry, you point your thumb in the direction that that is moving. So basically, at that instant, that coil is moving parallel to those, yeah, it's moving parallel. This is going to be confusing using the right-hand palm rule because we're not generating an induced EMF. We're not cutting field lines. So instead of considering it there, why don't we just consider, let me just get rid of that. Let's consider this spot here at 90 degrees, and then we'll also consider this spot at 270 degrees. So let's just think about this 90 degrees first. Let's use the right-hand palm rule here. So again, fingers point from north to south. So your fingers should be pointing to the right side of the screen. Your thumb is pointing in the direction that this part of the wire, the coil is moving, and this part is moving downward. So if you point your fingers towards the right side of the screen and you point your thumb downwards, you'll see that the current induced in here is in this direction. Really hard to see here. Let me maybe zoom in on this a bit more. You can see that the current is going in this direction at that time. Whereas over here at 270 degrees, if you point your fingers towards the right hand of the screen and you put your thumb up, you can see that the current in that very same piece of wire is now going the other direction. So the current is just now going this way in that same piece of wire. So the current has changed directions. And that's all that this is showing. This induced voltage, which will create a current, is just, this positive just means it's one way, and this negative just means it's the other way. And then if we finally look at this at the end of the cycle, 360 degrees later, so this gray piece of wire is again moving this way, which is parallel to the field lines. If it's moving parallel to the field lines, it's not cutting across them. It's just moving along one of them. So again, if we look down here, the induced EMF is 0 at that point. So hopefully that makes some sense. Down here is just another picture showing that whole process. You can see at this point, if it's moving this way, it's moving parallel to the field lines, and the induced EMF is 0. At this point, it's moving downward. It's cutting across as many field lines as it can, which is why we get this maximum here. And then again over here, 0. Over here, it's moving upwards. We're cutting across the maximum possible field line, so we're getting a maximum EMF, and then back here, it's back to 0. Okay, so if I were you, so that's the end of the presentation. If I were you, I would go on to this OneNote presentation and watch this video at the bottom. It's really good. It really goes through everything really well. And you'll see in the video, they use Fleming's right-hand rule. You'll see that they are going to use, it says right down here at the bottom, Fleming's right-hand rule instead of what we use, the right-hand palm rule. So I would suggest you watch that video, look at what the Fleming's right-hand rule is, how it works, but then understand that you can always just use the right-hand palm rule. It's much simpler. Trust me, you'll see. But watch this video because it's really well done and it really explains things, how an AC generator works. It really explains it very, very well. Okay, so I hope that all made sense for you. And I hope it wasn't too confusing. And if not, we can discuss it when we have our online sessions, which should be Thursday this week. So I will talk to you on Thursday about this, but please try that out and then try out the multi-choice questions that I've assigned on Google Classroom. You'll see it's a nice quiz and it's self-marking and explains all the answers, or it'll explain any answer that you got wrong. So try that out. I look forward to seeing all your results from that, and I will talk to you all soon.